Hello everyone. In this video we are going to discuss one of the most fundamental topics in the machine learning, which is regression, and in which we will be discussing linear regression and its types, i.e. multilinear and multi-target regression. The aim of this video series is just to give you the basic understanding and also to keep logs of my learning. Let's get started. So what is regression, right? Right now, I want you to think of it as a method to describe a relationship between two or more variables mathematically and use that to predict behavior of one when other is absent. This is very generalized definition. I try to summarize it a lot. You will get to understand it, or it will make sense as we move on. Let's take an example. Suppose you have a family with the 4 family members, right? And your mom is responsible to prepare food for everyone. She's been doing this since years, so she exactly knows how much food she will need to prepare for 4 people, right? For our example, 200 grams. Now, if you get 3 guests, how much food she will need to prepare, right? This is nothing but a regression, and it is surprising that she always gets it right. And how is she doing is that she has understand, or she knows the relationship of number of people and amount of food they are going to require. Of course, in real life there is too many things she is going to consider, and her intuition is going to play a major role, but this is a very simple example of regression. Okay, if your mom takes only number of people into the account to predict how much food she will need to prepare, then we call it a simple regression, right? i.e. 1x and 1y, we call it a simple regression. If your mom takes multiple things into the account, for example, number of people, their appetite, type of food they will need, and also the time of year, I mean summer or winter, she is taking multiple x into account to predict 1y, which is how much food she will need to prepare, then we call it multivariable regression. And if there are multiple y's she is need to predict, for example, she is need to predict amount of food she will need, variety of food she will need, all right, how much time it will require her to prepare, how many basic resources she will need. She needs to predict multiple things, i.e. one or multiple x or multiple y's. With multiple y's, we call it a multi-target regression. When you have to predict multiple output, then we call it multi-target or multi-output regression. Let's take an example. I give you this data set, all right? There is x and y's. Give me the value of y when x is 4. And yes, of course, most of you have guessed it, the value is going to be 8. And if I ask you to make me the equation for this data set, for equation for y, then most of you would have guessed the right, y is equal to 2x. And some of you may have done it based on by looking the difference in y's and difference in the x, or some of you may have just seen that this is going in even number. Either way, it is fine. And some of you may have took advanced approach, right? That's fine. And this is representation graphically. And what we are going to discuss in this video is going to be a linear regression. What I mean with the linear regression is that we are fitting this straight line on your data set. All right, we want only linear relationship. We are not trying to fit a data curve here. We are just trying to fit a straight line into our data set. All right, let's zoom into the graph. Initially, when I asked you to give me the value of y when x is 4, what I truly meant was stretch this line to the given value of x in order to receive corresponding value of y. That's exactly what we meant. All right, and here is your equation, y is equal to 2x, and this graph represents this equation. So you may be thinking, where is this 2 in this graph? And that is our slope. And I want you to think of slope as how tilted your line is. All right, slope is representation of how tilted your line is. Think of it as like that. Now let's take an example for the new data set. Again, predict the value of y when x is 4. Of course, most of you have guessed it, the value is going to be 9, right? Maybe some of you may, and I ask you to give me the equation, then most of you would have guessed the y is equal to 2x plus 1, right? Some of you may have just did it because of you were trained on the previous data, so you just took the difference, or some of you may have just added the 2, or some of you may have took this advanced approach. In either case, it is right. Let's represent it graphically. Let's zoom in. So this is your data set, right? 3, 5, 7. We have drawn a straight line there. This is your equation, y is equal to 2x plus 1, and this graph is representing your equation. So what is that 1, right? Where is that 1 in this graph? So if you stretch back your line, right, and you see it is intercepting y-axis on the 1, that is nothing but your intercept, right? I want you to think of intercept as how far your origin of line is from the x-axis. This is going to be very easy if you are going to understand that way. You can of course say the value of y when x is 0, right? But that makes less sense intuitively when you are going to think of it. I want you to think of it as how far is the origin of your line from the x-axis. That's what we want to know. So that is your 2x plus 1, and of course your slope is going to be there. Y is equal to mx plus c. This is the basic equation which we have learned in the school, right? Here is your slope, and which is nothing but the tan theta, so you got your value, which is 2. So now your graph represents y is equal to 2x plus 1. I hope you understand what I meant with the intercept, and to clarify it more, let's take an example here. So I tell you to represent y is equal to 2x plus 1 in this graph, right? You can, or there are data points I have already given. Our slope is 2. What it means is that your line is going to cross from the 2, direct 0 to 2. Well, of course, when there is the equal distribution at the both sides, your line is going to be crossing from 2. So let's just draw that, right? We have drawn our line, and now we have intercept 1, okay? And if you remember what I told you, it is the distance of origin of your line from the x-axis. So right now it is directly on the x-axis, right? The distance is 0, and what we want, distance is 1. So we are just going to drag it to the 1, and now your line is, your graph is representing this equation, right? Now, how do we know that our line is actually base fit line, right? How do we know that? Because in real life, you are not going to have a perfect positive correlated data. All are going to be in the straight line. That is not we are going to have. We will have this kind of noisy data. There may be a lot of outliers in your data set, right? So how do we know that our line or our founded M and C are the base fit line? So we can say first, what is a base fit line? It's that the Moore's number of dots is crossing, that we will call the base fit line. Yes, that is also right. Or we can say the line which is giving the lowest error, right? What is the error? See this this red dots, you can see these red dots are actual data set of your y's, right? And this blue line is our predicted y based on this equation. Okay, we found this equation, and based on this equation it is drawn. So what is our error? Is nothing but y actual minus y pred. How far it is, right? How far is our prediction? That is your error. And there are measures of error, which is, we call, one of them is mean squared error. What we do is just we take a difference and we square them. The reason why we square them is because we are going to have minus values here. Here our predicted y, here our actual y is greater than our predicted y, so we are not going to have any kind of minus here. But when you look at this side, when our predicted y is more than our actual y, you will get the answer here in the minus. And what will happen is that this all summed up error is going to get now minus from here. This all are going to minus from our summed up error. That's not what we want. We want to have an absolute error, right? We want to see in absolute terms. So that's why we are squaring them. There is also another which is we call R square. There is also a lot of MAE, mean absolute error, in which we are not squaring anything, we are just taking absolute value. Even if there is a minus, we say it as plus. That's there. Don't worry if you don't understand right now. This is just to give you the overview, all right? Now let's take, this is one data set. This is, can you fix what I mean here? Can you apply a linear regression into this data set? Yes, of course, you can apply linear regression in data set, because visually you can see how your data is going, right? And suppose if I give you this data set, can you fit a linear regression there? No, because your data set is too far ahead from each other. Even a polynomial regression is giving the R square of 66, right? Yeah. The reason why I am showing you these two graphs is because in real life you are going to have this kind of data set, and you will need to decide which algorithm you should apply. Yes, it is going to be simple from your question that you are looking for regression or classification or noise reduction. It will be easy to, it will be simple from your question, but in regression which algorithm you will use, in classification which classification algorithm you will use, is going to be dependent on you, because you are the one who is going to decide that, right? So how you will decide? You look at the data and you think of it as, does this algorithm apply here? And you can only do that when you know how those algorithm works. Let's take an example on another data set. These two are exact same data set, just here I have fitted the polynomial line and here I have fitted the straight line, right? Linear regression, and this is polynomial regression. You can see the difference in the R square. Well, of course, because we are bending this line corresponding to the values, right? And here we are just straight fitting it. So now you may have question, how do we find value of M and C when we have this kind of data set, right? It is not going to be easy. We are not just going to guess it like we did it previously. So there must be some sort of way. What do we do, right? So what should we do? Well, first of all, we can do a brute force, right? But, well, everyone knows that that is a wrong idea to do a brute force. Or we can use some kind of formula, right? So let's go with the formula. Okay, again, I am giving you this data set. Of course, I should have given you the real life data set, but it will be harder to understand the equation based on that. So that's why I kept the calculation simple. That's why I give you this. And we have this equation. Don't worry, we will derive this equation and I will explain what they means. But right now, just think of this equation. What we are doing, we are taking a deviation of x from its mean and y from its mean, right, and dividing it with the variance of x. This is what we call a covariance. Okay, what covariance means is that how much combined effect those two x and y are giving. In very simple terms, I am generalizing a lot. So how much combined effect these two are giving together, right? And once we divide it with the variance of 1, then we will get the answer respect to that particular variance, our slope. Okay, I don't want to make it complicated, so let's get started. So our mean x is going to be 2.5, right? Our mean y is going to be 6. So we are going to sum them, 1 minus 2.5, right, into 3 minus 6 plus and dot 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 dot, and you will have particular answer for your covariance, the sum. So it is going to be the 10, right? Yes. Now what we did, look at here. You may think that why do we do that when we can just simply divide the deviation of y with the deviation of x? Yes, of course you can do that, but you will need to take absolute values, right? Do it now. So 3, 1, 4, 1, 5, 3, 8, 0.5 to 1, 1, 2, 4, 8 divided by 4, your slope is 2. Yes, of course, that is also correct. Sorry, I forgot here. This equation is for the slope. I forgot to write here m. All right, this is the equation for the slope. Okay. Now let's take the deviation of x and deviation of y. Of course, our equation shows only variance of x and variance of y, but we are going to take also for y because I want to show you one thing. So it is 5 and it is 20, right? And if you divide with 10 by 5, you will get the answer 2, which is respect to the yx, right? Y is equal to 2x. That's what this equation means. Or why does that happen is because you divided the covariance with the variance of x, right? If you divide it with the variance of x, you will get answer with the respect to the y. And if you divide it with the variance of y, you will get answer with the respect to the x. As you can see on your screen, right? 10 divided by 20.5, x is equal to 0.5y. That is why I just also calculated this. Otherwise, there was no need. So now let's find our c. Y is equal to 2x plus c. So c is going to be y minus 2x, right? But we have multiple x and multiple y's, so we just take a mean, all right? Also, this equation also have a proof, but right now you can logically think easily that yes, of course you will need to use a mean, right? Or you can take a multiple c's and then take a mean. That is also going to give you the same results, right? We take a mean and you got our answer, which is y is equal to 2x plus 1. All right. Now let's move on to the another topic, which is what we call a gradient descent. Keep that in mind. This is not the part of this video. I just added to inform you that there is something this exists, right? You can see what we are doing in gradient descent is that we will change the value of slope and c depending on the value of MSE or our error, and we will try to fit a line where the error was the lowest, right? Wait, let it just restart. You can see, observe it now. See, MSE is decreasing as well as our M and C values are changing, right? And of course, code I use for this animation is here. I will add it into the Jupyter notebook. You can use that, but keep that in mind. I will explain gradient descent into the another video because I was very confident when I started this video that I will be able to make animation in Google Slide, but I was wrong. So I decided I will explain gradient descent into the another video because there are multiple types also with how. So let's derive our equation. We have our equation y is equal to mx plus c, right? And what we want to predict y based on given the input of x. But in order to do that, we must have slope and intercept, right? Another thing, in reality, what we are actually aiming for is actual y minus our predicted y is equal to be 0, right? What it means is that error is our prediction was so perfect and it was perfect near to the what was actual y, so if we remove them we got the 0. That's exactly what we want, right? So let's write it in the error form, which is we have MSE, mean squared error. If you are taking MSE, then your workload is pretty hard. If you are taking mean absolute error, mean absolute square, MAE, yeah, then your workload is very small. What I mean here is that y minus y pred whole square sigma divided by n, and here it just y minus y pred sigma divided by n, just that. So why we are squaring here is because there is going to be a minus values, right? Let's say you have your data set like this. You have this data set and your line is going through that. So what we are this equation saying y minus y pred is just that, right? So it is on this side, so it is going to be positive error, right? Yeah, fine. But wherever this is on downside, it is going to be in negative because our y pred is higher than the actual y. So if you look here, y pred is higher, so we will get in the minus. Okay, so what will happen? Our previous all summed error will get, and this one is going to get minus from them, which is not good, right? Because what we want to have an absolute values. We want to have absolute difference and then we are going to divide. We do not want the direction right now. Okay, so you can use this formula and say absolute, then it will work exactly as this would have worked. But np dot, I don't know if we can just say np dot absolute, like kind of like that, but we will figure out. Let's solve this here. All right, so we have our MSE equation. We want to have it as 0, so let's write sigma n y minus y pred whole square is equal to 0. That's basically what we want. No, here it is n. No, don't worry. All right, now if we look at the equation, y prediction would have kind of like this. We will have the value of y, of course. So y prediction value, how we are going to find is mx plus c, right, whole square. If we look at it now, there is a square, right? Let's just remove the bracket also. So there is a whole square. So if we are going to do it with arithmetic way, then it is going to be much tedious. And also there are two unknowns. So how we can do a partial derivative. So what does partial derivative does is that we in simple short terms, we make other thing as a constant and keep one thing which we are trying to find a partial derivative, and same for next time. And there are rules is that first you take for the outer function, which is our square, and keep your inner function as it is and multiply, then you go for your inner function. All right, so let's just do it in the respect to the c. So what we will get, so first there is 2, so 2 is going to be here, 2 sigma n y minus mx minus c, right? So that's there. Now we want to look at inside. So what we have in inside function, let's see. There is a c. Oh, okay, sorry. Is there a c? No, so 0. Is there a c? No, so 0. Is there a c? Yes, so minus 1, right? So we are going to multiply this entire equation with the minus 1. Okay, so means minus 2, but again here is 0, so it is in multiplication. We just shift it to the 0. Boop, it's removed. So we will left with sigma n y minus mx minus c, right? And now if we add this inside, sigma n y minus sigma m is constant, right? So and here is going to be i's. I forgot to write the i's. Of course, we are iterating. We are not doing on entire data set. We are iterating through the data set. Okay, we are iterating through the data set. yi, xi, and again c is a constant, so this entire sigma value is going to be the 1, so we left it here. What does this mean? This is yi, right? Your 1y divided by n on sigma, entire data set. We are summing the entire all y's and then dividing them with their length or ln x or degree of freedom. So what we get y mean, right? This is the formula for y mean, or sorry, any kind of y mean, it is the formula, right? So we can just write it here, y bar minus mx bar minus c. So if we want to find for c, then c is equal to y bar minus mx bar. All right, so this is our equation for the c. Okay, now let's go for the dm. Where was our original formula? Yeah, here it is. All right, so let's derive for that. I'm going to do directly by looking here. So first let's take a minus 2 ahead, yi minus mxi minus y bar minus mx bar. Okay, I have added the value of c directly. All right, now again this 2, send it to the 0. Boop, we removed it. And now what we have, now let's do for inside function. Or first we should, okay, first solve this equation first. Before doing anything, let's just clarify it. So what we will have, yi minus mxi minus y bar plus mx bar. And if we, okay, y minus y bar, we are grouping them, minus mxi plus mxi plus mx bar, so it is going to be a minus mxi minus x bar, right? So our final equation would be sigma n yi minus y bar minus m xi minus x bar, right? So that's our equation. Now let's do that. Okay, we already did for outer function, no, not to worry about that. Now we are doing on the respect to the m, right? So here is no m, so 0, and here is m, and m have xi minus x bar, right? Minus, so we either way we are sending minus that side, because see, if here is a 0 and I am sending them there, it actually doesn't matter, you can do that, but sigma n, and there is an xi minus x bar, yi minus y bar minus m xi minus x bar. All right, I can send this to the there and directly remove it, but let's just keep it there, because when I was doing manually, okay, let me show you both way. All right, we removed it. Okay, so boop to the 0, boop to the 0, then we will have other way. So what we have y, okay, so yi minus y bar, right? And we have minus m, this is not there, so minus m xi, minus m goes there, yi remains there, m is going to be positive, so this is multiplication, this goes down, so what we will left with, yi minus y bar, sigma is always of course there, divided by xi minus x bar. This equation is also right, and the previous equation what we've seen was this, right? Xi minus x bar divided by xi minus x bar. That was, here was square, so I expanded, right? This was the actual equation. Both are saying the same thing, all right? Well, we are standardizing our y's, we are standardizing our x, we are standardizing our y's, we are standardizing our x, and then we are dividing them, so we will get the slope in between. So that's exactly, this one is also right, but if we are going to use this, you must say these are absolute. All right, and if you are not going to do that, then let's keep that, don't remove it. So what we will be left with inside, that would going to be yi minus y bar, xi minus x bar, minus m xi minus x bar, xi minus x bar. All right, that's there. And if we do for the m, then m is yi minus y bar, xi minus x bar divided by xi minus x bar whole square. All right, just whole square. It is the same thing. And if you are going, if you are going to remove them, then again you will get this formula. All right, in statistical way, what we call this two is a covariance. All right, and we call this as a variance, of course. If you remember, we have solved over these equations. Okay, now I also want to show you a matrix form. Matrix form is because we can do multiple calculation at once. Matrix form, all right, matrix form. So again, we have this our equation y is equal to mx plus c, all right. And in the matrix form, what we can do, we can store all of our y's here, all of our unknowns here, right, and all of our x's here. And we can either, it may be multiple x, or it may be like you may have equation is equal to y is equal to m1 x1 plus m2 x2 plus dot 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 plus c. So you can store all of them here, you can also store all of x's here. And even if there is a multiple y's, all right, in your data set, if you have a data frame, and in data frame you want to have this 2 column as a y's and this 2 column as a y's, then you can also store them here. So if we came up with the matrix formula, then we can do all kind of calculation with the single formula. Even if it may be a linear regression, it may be multilinear regression, it may be multi-target regression, we could be able to do that with the single formula. All right, so let's just go with it. Again, what we want to have yi minus y pred is equal to 0. That's exactly what we want, right? But if we talk in the MSE sense, then this is called sum of residual sum of square divided by n, or degree of freedom. I don't understand this part. All right, see, what these are saying is basically this e square, right, error squared of error divided by n. All right, so what happened here, I was googling and I found two documents. They were saying that e square in the matrix form, as it is a vector, or sorry, see, MSE is not a vector, it is just kind of like, I don't understand why, but they have said that we can write it like this. All right, I will add the reference to that, and also checked the Stack Overflow for this, and they were also saying, but I did not understand. I don't understand matrix at all right, so they have said that you can write it like that, and someone was explaining kind of like this, that if you transpose one and if you do that, uh, and it is kind of like a value will be scalar, not a matrix. That's what ChatGPT said. All right, and this is kind of like a near to e square, but I don't know how we are going to do kind of like that. But again, so I see, don't take me on this one. This is not from my side. I have just watched it and I have googled it, kind of like that. So transpose, so first what we have, all right, now let's look at here. What we created here is just nothing but x beta, where we have stored all of our betas. Beta means all of your unknowns. All right, all of your unknowns. If there are multiple, then multiple, all of your unknowns there. So let's add the value here, y minus x beta transpose into y minus x beta. All right, now there are a few rules which I googled about the matrix multiplication, or not general matrix manipulation rules. So right now it is going to be transpose, right? But here, if we are going to add this, then we need to shift the order. All right, beta and x, and then we will have a transpose. All right, and now we have y minus x beta. Okay, now let's solve it. Let's expand it. So yt into y minus yt into x beta minus beta t x t y. Okay, then minus minus plus beta t x t x beta. All right, we have this our equation. Now let's derive it in the form of d beta, and of course it is going to be the 0 at this side. Okay, now let's observe this too. Okay, they are essentially the same thing, right? One is transpose here and two are not, and two are transpose here and one is not. So either way, if we transpose any one of the matrix, they are going to be the same, exact same results. Okay, and also this step is also not done by me, or I don't understand how this works, but I'll just read it into the document, y minus y. So what we will have left with is that, see, x beta, and if we transpose it, what we have left is beta t x t y, right? What if we transpose this, then we will have that. So they just directly said that beta t x t y, right? Now here, see, this is the matrix rule. We have our beta t here, and then there are a's, and then there is beta. So what we need to do is we just say add 2 and keep this part as it is, x t x beta. That's what we do. All right, and sorry, here it is going to be the 0 because we were doing that and I forgot here. So it's 0. All right, we remove the 2, it's going on, and here is 0. So now we have beta, and this is in the minus. Let's shift it there, beta x y, sorry, 2 beta t x t y. All right, sorry, there is not going to be beta t. The rule I applied here is going to be applied here also. See, all right, there is not going to be any beta, so there is an x t y. Okay, and then we have x t beta, x t x beta. So beta is going to be x t, x goes there, x t x inverse. If they are jumping this is equal sign, then it's inverse, then into x dy. So this is your, okay, let me write it properly. Beta is equal to x t x whole inverse into x dy. Okay, so we derived our equations, and now what I want you to know, okay, just simple thing, and we will move on to the coding part. But you see, in our equation, what we have mean, right? Our all equations are using mean. So what does that indicate is that, listen, wherever in any equation you are going to see the mean, that equation is extremely sensitive to large numbers or the outliers. All right, if you know the behavior of mean, then you probably understand what I mean here. Let's take an example. You have this data set, right? And you can see here is one outlier 39, which is not matching. The energy of this is not matching with any one of them, right? And also we don't have next values to see that, okay, it is jumping here, right? We don't have next values, so we cannot be sure. So these two are outliers, right? This one and this one. What will happen is that when you take a mean of it, this entire data set is going to shift upwards. Okay, for easy understanding, let me give you the example. Suppose I give you the 6 people's salary, all right, 10,000, 15,000, 20,000, 30,000, 90,000, and I ask you the question, how much one person average earning, right? What is the earning of one person average? Just give me random number, but make sure that it accounts all of people. Then you can take a mean and your answer is going to be 30,000. But if you look at the data set, that makes no sense at all, right? Does this make sense? No, because only 4 people have, and only 1 people have 30,000 and one has the higher than 30,000, yes. But only 4 people don't have 30,000, right? So what you can do, you can either remove this 90, right? You can either remove the outlier from your data set, and now if you do the calculation, right, divide by 5, then you will get the answer 18, which is much more sensible, right? Which is, you can say, yes, that number is okay. You can say that everyone is earning 18,000 average, right? Or you can take a median, but of course you cannot replace median here. So you can replace the value of 90 with the median, or outlier with the median, or the best way is just to remove them. Or you can do train one model with outlier and train one without the outlier, compare them and see which one is better. All right. So now let's make algorithms in Python. You will find the source code here. All right. I will put the link into the description. This is where you are going to find the source code. And if you go into regression chapter 0, you will have our Jupyter notebook and dataset. So let's get started. I have already coded the model because of if I was going to live code, then video would get very long, and which is unnecessary. I have wrote the equations here, and you can see what I want you to do is implement this algorithm by yourself first. And when you let's say you cannot able to do that, only then come back here and see how I implemented it. Of course you can implement it however you want, right? As long as you are applying the proper formula, your implementation is going to be right. So first let's import basic, right? Panda, numpy, matplotlib, because it is unnecessary here, but I also want to show you how to save the model which you have created from the scratch, right? This is our data set, right? Let's understand the data set. So what we have in our data set is that the interest rate and the median home price, right? You can observe that I want you to predict the median home price depending on the interest rate, right? You can of course use years also, but years is not describing anything numerically, right, other than just they are increasing, so we did not took them into the relationship. I want you to predict median home price, but now let's observe the data more, right? You can see in our data set we have dollar signs, right, and also comma. So our model is not going to comprehend that, right? So we need to remove them and need to convert into the pure number. So that's what we did here, str.replace. You can of course use panda's apply method with a lambda, but it was very simple, so I just used this method. Now let's understand the data set. Data.info, now you can see we have all numbers, right? Integer, float or integer, they are numbers, okay? And what we have in describe method, you can see count is 16, we have our data set is 16 and all are 16, so there is no missing value, right? And we can see the mean, all right, we have a mean value, standard deviation. Well, standard deviation with the interest rate is kind of very low, okay, and the standard deviation here is pretty high. If you think that there is only going to be 1% change in interest rate, like 10 and 11, then here it is like 5,000. So it is kind of relatively high. So model is not going to be that good if you look at the data set, right? And here is your max values, okay? And this is the correlation table. Whenever you are going to do a regression, linear regression specifically, make sure to do a correlation coefficient. It is very simple, data.core, and you will get the correlation coefficient. What is our y is median home price. So let's see, our interest rate has 0.62, right? Negative 0.62. What it means is that as interest rate is increasing, the median home price decreases, and the vice versa. And you can see here also have the relationship. Of course, one to keep that in mind. These formulas don't understand what you are feeding it, so it's up to you to decide whether to take this relationship into account or not, right? Here is describing nothing, so we cannot just take into the account. Of course, you can train the model, and if it works much better, then it's fine, right? So let's just plot it to observe the data more. I just said data.plot kind scatter, x is our interest rate, and y is our median home price, right? And you can observe this data is very bad. You cannot fit a straight line and get the proper results, right? You are not going to have the proper results. Either our straight line is going to fit here, or it is going to fit here, because if it is fitting here, then the distance is very high, so error is going to be very high. You can remove these outliers, of course, but then it will make no sense, because our data set has only 16 entries. So that is also one problem, right? Our data set has only 16 entries. That is one of the big problem. But we are just testing our algorithm, that's why. So let's say our x and y, right? And now let's create the model. So this is the most important part of this entire thing. I want you to use your own data set, all right, but the model code. So I created the class named linalg, and in which we have fit method, right? So which formula I'm using is I'm using covariance divided by variance. So that's there, and it's pretty simple. I don't need to explain this code, right? And I have added the self.m_none, and that's there. We predict and evaluate. I use the R-square, and in the save I use the pickle to dump entire our model with the train values into the .pickle file. It is not safe to do that, because when you are just going to load the model back and you are going to predict, someone can replace that file and add malware in the predict function, and you will get hacked. That's one of the major problem here. So you can just store this in the plain py file and store our dictionary, which is self.m and self.c, into the another file. You can do that, but I am keeping like this. It's easy for me. So this is our model. Let's just train it, evaluate, and see our dict. So which is R-square is 838%, which is very bad, right? And of course our data set was very bad. And our m is minus, okay, our slope is in minus, our c is also pretty high. Our data set is starting from pretty high. Let's compare it with the sklearn model. Our model did good or bad, right? So R score is the same, right? Our R score is the same. Our coefficient is nothing but a slope is also same, and our intercept is also same. So our model is based what it can do on this data set, right? Given the data set. Let's plot it. So you can see our model is fitting only one. Our line is fitting only one dot, and that is also because here there is a lowest error. All right, here there is the lowest error. If the line was fitting here, then error was too high. All right, so that is your linear regression. Now we go with the multilinear and multivariable regression. This is your equation, right? Y is equal to m1x1 plus m2x2 plus dot dot m and x1 plus c. And for the beta, we derived this equation transposed x into x, they are inverse into transpose x into y, right? So let's get up the data. I already added the data, observed the data. In data, you can see city is kind of like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we don't want to include that. You can include that if you want, but what this data is for, that there are number of population, number of weekly drivers, right? So population of city, monthly income of drivers and average parking rates per month. Okay, I want you to take to kind of do like what I have done here. Let me show you what I did. I just observed the data. All right, that's not the main part here. So I take X as a number of weekly Y as a number of weekly drivers and population of city. All right, I want to predict number of weekly drivers and the population of city, and want to give other thing as a variable X, right? Price per week, monthly income of driver, average parking rates, right? So logically you cannot do kind of like, you cannot use average parking rate per month to predict number of weekly drivers. Or maybe yes, we can use it may be costlier or cheaper, and that will, yeah. So number of driver we cannot use this, but I just used randomly. You can train however you want, but what we are doing here, I am taking multiple X and multiple Y's. This is multi-target regression. If we are going to do for multilinear regression, then just remove this from here, right? Just remove this and also from the X, and you will have your multilinear regression. We took that, our code for multilinear regression. It's pretty simple. We are applying the same formula, right? Here just see why I added the ones or C is because in our beta I want to get calculated our intercept also. So we added the intercept value 11111, right? So we added len x1, we reshaped it, and then we concate the x with the C with the x on the first position, right? So x is equal to self dot add x, that's there. And our slope formula, which is pretty simple, np dot these two, then inverse them, and then multiply with these two. So our equation, our answer will get our slopes, or I should have said coefficients rather than slopes, but it's fine. So our self dot m is going to be after 1, right? After 1, and our self dot c, which is our intercept, is going to be at the first position because we have added it into the first position. And self dot predict is going to be the same, y is equal to mx plus c. That, so it is pretty straightforward. And if you can see, our model is performing well. We have our values, right? Minus 719, minus 550. These are all your m's, and this is your intercept. Okay, wait. Yeah, because this is multi-target, right? This is multi-target, that's why. Otherwise I was thinking why there are two values of intercept, but this is multi-target. So if we evaluate our error is that, all right, let's compare it with the sklearn model. All right, let's see the dictionary of sklearn model. We can see our coefficients are the same, right? Our coefficients are the same, and our intercept is also the same. Our intercept is also the same. So our model is doing perfectly fine as much it can do here. And this is just, I created this data frame to see the comparison visually, how much difference is there, right? A dot is actual and P dot is our predicted, right? So you can see that, and that is our end of this video. All right, I hope you can use this knowledge on your own data set. All right, see you in the next lecture, where we are going to kind of, I am deciding to implement this into the Godot to also show you that we can use if we learn it from scratch, we can apply it anywhere mostly. Of course there is not going to be a numpy, but we will be able to do that, right? So let's end this video right now. Next time we will be doing on the gradient descent.